Well, good afternoon. Sorry, I'm starting way late. My last class, one of the students needed a break in the middle, so I thought, well, let's just take a quick break. And it wasn't very long, but I came back refreshed, and we got on a roll and then went way past the time. So sorry about that. And now I just took another little break to get started again. So sorry we're so late getting started here. But no one else is in the room. It is 2:24 on Wednesday, the 1st of November, All Saints Day. And it's supposed to be differential equations, and right now I'm the only one in the room. So let's get going where we left off last time. Now, you won't hear this in time to do anything with it, but my office hours today, I've got to leave right at 3:15 or as soon after this class is over with as possible. This has been a terrible 2 weeks for vehicles for me because I had one die on me, and then I've been scrapping around trying to get it fixed. We finally gave up and said, look, just going to need the new vehicle. So we got rid of the last one, the old one, on Monday, and started the process of getting a new one. We had planned to get it on Friday. The dealer called yesterday and said it was ready and wanted us to pick it up today. Unfortunately, he's up in Jasper, so we've got to run up to Jasper and pick it up, and he leaves at 5:30, I think he said. So we've got to leave, right? I've got to leave here, head to Birmingham, pick up my wife, and then head to Jasper. So I've got to leave right as soon as this class is over. So I'll try not to go late on this class, even though we're starting late. Sorry about that. All right, so let's pick up and go from here. We're in Chapter 4, Higher Order Differential Equations. We had just done Example 4 on page 123. 4.1, by the way, is Preliminary Theory, Linear Equations, and we're on linear dependence and linear independence. The next two concepts are basic to the study of linear differential equations. All right, here's what we got. Definition 4.1.1. Okay. A set of functions. Oh, yuck. Okay. Forgot to get my pen activated. Okay. I think I've got it now. Yeah. Okay. A set of functions, f1 of x, f2 of x, f3 of x, dot, 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 all the way up to f sub n of x. Okay? They are said to be linearly dependent first. Okay? Linearly dependent on some interval I. Okay? If there exists any set of constants, C1, C2, C3, dot, 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 up to Cn, C sub n, not all zero, okay, such that, sometimes that colon is used as such that, C1 F1 of x plus C2 F2 of x plus C3 F3, oops, C3, put my parentheses in the wrong place, F3 of x plus dot, 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 plus C sub n F sub n of x is equal to 0. Okay? That there is some set of constants that when you put these together and with those constants, you're going to wind up with 0. Now, that certainly would happen if all those c's were 0, okay? But if there's some set without all of them being 0 that makes it 0, then this is a linearly dependent set. And this has to be true for all x in the interval. Okay? Now, if the set of functions, if some set of function okay, is not linearly independent and not linearly dependent, then on the interval, then they're said to be linearly said to be linearly independent. Okay, now it's sort of, some ways a little backward seeming or double negative seeming or something, okay? If there is some set of C's, other than all C's being 0, that you can make that set of functions add up to 0 for any x, every x in the interval, okay, then that's linearly dependent. But if there is no set of C's, that when you combine them together, any set whatsoever, except all C's equals 0, that can make that equal to 0, then it's said to be linearly independent. Okay. All right. I'm so glad there's someone here for me to talk to. Okay. I get sort of bored talking to myself.
You want me to switch the lights?
Yes, please. Okay. Now I can turn on the projector for you. Okay, I just finished writing something really ugly. Not ugly in the sense of mean or anything, but my writing stinks. Okay. I'll have to wait till that comes on. No, it's too late. No, I'm just kidding. Okay. Oh, no. Lose the 10. Okay. S2. All right. If you're wondering why we didn't get any further, in my last class was Cal 3 class. We don't start that class till 12:15, and it's supposed to go until 1:55, and this one started at 2. Well, one of my students, a little over midway through it, just had to take a break. Had to go to the restroom or something, and my throat was awfully dry, and so I said, "Yeah, let's just take a 5-minute break or less." And we were back. She was back in less than 5 hours. I think back in less than 5. It seemed like someone stopped me. I stopped. Thought I needed to give something to somebody, but it turned out being the wrong person. But anyway, back real quickly. But then once we got going again, it was like fresh start. And suddenly I looked and we were 15 minutes into this class. I went, I just run over. So we didn't get very far along. And I've got to leave at 3:15 today, so sorry about that. Okay. Talk about linear independence and dependence. So are you familiar with the concept? Yeah, okay. So if there's a set of functions, they're linearly dependent if you can come up with some set of coefficients for them, without all of them being 0, of course, such that the C1, F1 to C2, F2 to C3, F3 to C4, all the way up to Cn, Fn, that some group of coefficients that you add those together can make that sum equal 0. If you can, without all the C's being 0, they're linearly dependent. In other words, some 2 or more of them are combinations of others. Okay? That's linear dependence. That's for all the x's in that interval I. If the set of functions is not linearly dependent on I, then it's said to be linearly independent. In other words, there is no set of constants that you can put together except all C's equal to 0 that you can get that to add to be 0. In other words, every function is independent of the other functions. They're not multiples or combinations of multiples of them. That's what linear independence is. In other words, a set of functions is linearly independent on an interval I if the only constants for which those will work are all the constants being 0. Okay. Now, oh, yuck, that's not what I want to do. Okay. Keep forgetting which class this is. All right. Now, it says it's easy to understand these definitions for the set consisting of two functions, f1 and f2. If the set of functions linearly dependent on an interval, then that means that one of them is a multiple of the other. Okay, that's the only thing. If this function is here and the other function is there, they're dependent on each other. Okay, there's some way, or even like this, then they would be okay. But if they're like this, there's no way that those are going to be linearly dependent. They've got to be independent. Okay. Or if f of x is equal to the identity function x, okay, y is equal to x, and then the absolute value, y is equal to absolute value of x, okay? They certainly aren't dependent because you can never get this out of that. So those would be linearly independent also, okay? Now, if you restricted the domain to be from 0 positive, yeah, they are definitely linearly dependent on each other. But if you have all real numbers, yeah, they are linearly independent. Okay? If you only had the two functions, then if A is a set of two functions linear dependent, then one function is simply a constant multiple of the other. Okay? When you get more than two functions, then it gets a lot more complicated to see, but with just two, one's a multiple of the other. So let's do example 5. Here's a set of functions. f1 of x is equal to cosine squared x. f2 of x is equal to sine squared x. f3 of x is equal to secant squared x. Secant squared x. Okay. And f4 is equal to tangent squared x. Okay. All right. Now, in the first case, okay, this set, the interval on which you're talking about, has to be between minus pi halves and pi halves. In fact, not including either endpoint. Any idea why? Second? I can't hear. I can't hear. Not 0. Secant and tangent are not defined as minus pi halves and pi halves. They go to infinity. Okay? So, therefore, you have to be within that. You can't even cross that. It can't be between pi halves and pi. I mean, between 0 and pi. No, because you got a discontinuity, a huge discontinuity there. So, yeah. But in that interval, are they independent or dependent? Okay? Let me just make an observation here. What is cosine squared x plus sine squared x. Okay, that one's 1. Always. Sine squared plus cosine squared is always 1. Think of it this way. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And you square this opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. That would be opposite squared plus adjacent squared over hypotenuse squared, right? What is opposite squared plus adjacent squared? Right angle. Hypotenuse squared. That's 1 over 1. Right? Okay. So that's always 1. Frankly, here's another rule, okay? If you divide each one of these by cosine squared, okay, what do you get? 1 plus tangent squared is equal to, which is secant squared. Okay, right? Now, from that equation, we can subtract the tangent squared from both sides, right? And that gives us that secant squared x minus tangent squared x is equal to 1. Right? So guess what? We can do sine squared x plus cosine squared x minus or plus tangent squared x minus secant squared x, and that's going to be 0. Want it? Because these two add to be 1, and when you reverse these two and make it tangent squared minus secant squared, that's going to be minus 1. And plus 1 minus 1 is equal to 0. So there you have a set of C's. 1, let's see, yeah, 1, 1, 1, minus 1, 1. Okay? That will make that be 0, and none of those are 0. Okay? Well, that was just sort of easy to do that way, but yeah, those are not linearly independent, they're linearly dependent. Because there is a set of C's, 1, 1, minus 1, 1, that when you combine those 4 functions together, you get 0, without all the C's being 0.
Can you explain that last part?
The which?
The last part.
Okay.
The C.
About the
C. The coefficient.
The coefficients, right. You see, here's function 1 is this one, function 2 is this one, function 3 is that one, function 4 is this one, right? Now, to be linearly independent, there must be no coefficients that you can put together of those 4 functions that could ever be 0 unless all the coefficients are 0. So therefore, if there are some coefficients that you can combine those together to get 0, it can't be linearly independent, so it must be dependent. Well, here's the coefficients. 1, 1, minus 1, 1. Okay? Those are not all zeros by any stretch. In fact, none of them are 0. But when you add those together, you get 0. So obviously, there is some combination of coefficients of those functions that will equal 0 linearly dependent. That's what it means to be linearly dependent. These functions are not completely dependent of each other, independent of each other. Not all 4 of them at once. Okay? All right. I don't know if that's the example they do. Yep, they said C1 and C2 both 1, C3 negative 1, and C4 1, yeah. All right. Now, another way of saying that, a set of n functions, f1, f2, f3, up to fn, is linearly dependent on an interval I if at least one of the functions can be expressed as a linear combination of the remaining functions. Okay? It's another way of saying the same thing. And this, for instance, again. Okay? All you have to do is add secant squared to both sides. And you have secant squared, which is L3 is secant squared plus cosine squared plus tangent. It can be written as a linear combination of the other functions. That means it's not linearly independent because it can be written as a form of the other three. Now, once you get down to those three, I think they may be linearly independent. I don't think there's any way in the world that you can combine those together and get 0 for every x in the domain. That's true for every x in the domain. Okay? So the 4 of them are linearly dependent. The 3, I think, would be linearly independent. Okay. All right. So if you had just 3 functions, but they were dependent of each other, then you could say f sub 3 of x is equal to some combination c1 f1 of x plus c2 f2. I do that about half the time. Somewhere in the process I put the parentheses in the wrong place. I get there thinking faster than I can write. F2 of x. Okay? If there is some constant that you can express this one as a linear combination of the other two, then obviously if you subtract this from both sides you get 0. That sum will be 0 if all those C1, C2, and 1 are not 0. Okay. All right. So let's do example 6. All right. Here's a set of functions. f1 of x is equal to the square root of x plus 5. f2 of x is equal to square root of x plus 5x. Okay? f3 of x is equal to x minus 1. Okay? f4 of x is equal to x squared. Okay? It tells you this is linearly dependent. Okay? On the interval 0 to pi, 0 to infinity, on the interval 0 to infinity. Okay? Now, why? Okay? Well, this function has a square root term and a linear term. So I'm guessing there's some way that you can write F2 as a linear combination of those two. Okay? This one's not in the picture at all. Okay? This one is independent of any of the others. It doesn't get into play at all. So don't even mess with that. But this one. So let's see what we can do. square root of x plus 5x. Let's see if we can come up with some combination of c1 times square root of x plus 5 plus c2 times x minus 1. Now I just picked on that one because this one has a quadratic, a root term, a radical term, and a linear term. This one has a radical term, that one has a linear term. So I'm guessing there's some combination we could do. Let's see if there is. Okay?
Are you using an x, c1 square root of x plus 5x, or
Okay.
you're doing the first?
Okay.
So you're doing f1.
Okay. In other words, what do we name the c's? Is that what you're saying?
You're setting f2 equal to f1 plus f3.
Yeah. So if are you wanting to name that C3?
No, I'm just asking.
Yeah. The F2 is some linear combination of F1 and F3. That's exactly what I'm saying. Now, what subscript we use on the C doesn't matter. Okay. I thought that's what you're asking first. Just because that's F1, that's F3, so me a C3 there. And yeah, you can name it C3. You can name it K. You can name it Fred. You can name it anything you want. Okay. It's just sometimes. Okay. I'm just making that guess because you see, this one has a quadratic term, a root term, and this one has a linear term. So I'm guessing this can be written as some linear combination of those. And let's see if we can. Okay? Well, this would be C1 root x plus 5C1 plus C2x minus C2, right? Okay? Now, according to what we've got here, C1 must equal to 5. Must equal to 1. Okay? C1 has to be 1 because that's the only coefficient over here of that. So let's say C1 is equal to 1. Okay? And C2 must be equal to 5. Okay? Now, does the rest of it work out okay? If C1 was equal to 1, this would be 5 minus 5 is 0, and sure enough, that works. Okay? So, that is we came up with some constants, C1 and C2, both of which are not 0. Well, actually, they could be 0, okay? Some constant C1 and C2 that can make that work. And sure enough, that was it.
So if you write it the other way, where you add them all together and it has to be equal to 0, you would just put a 0 on in front of f4?
Yeah, exactly. Because guess what? None of those have an x squared term in it, and yeah, there's no way it's going to even enter the picture. It's linearly independent of all three of the others. Okay? Because you can't combine those together and get it. Those three you can, though. Okay? All right. Good deal. All right, that's example 6. They just pulled it out of the air. C1 1 and C2 was 5. Said, hey, look, that works, But now you see why it works. Now, solutions of differential equations. We're primarily interested in linearly independent functions, or more to the point, linearly independent solutions of linear differential equations. Although we could always appeal directly to the definition back there, it turns out that the question of whether a set of n solutions, y1, y2, y3, up to yn, of a homogeneous linear nth order differential equations is linearly independent can be settled somewhat mechanically by using a determinant. Okay? Yay. You've had linear algebra, right? Yeah. Okay, I thought you did. So you are familiar with determinants. You may have been familiar with it before. And this particular determinant we're going to use is called the Wronskian. spelled W-R-O-N-S-K-I-A-N. Before the, what is the name of those sisters that are in the news all the time? Kardashian? The Wronskians were the big thing. No, I'm just kidding. Okay. All right. So let's say that we have n functions. Okay? F1 of x, F2 of x, F3 of x, all the way up to and including F sub n of x. Okay? Now let's suppose that each one of those functions has at least n minus 1 derivatives. Okay? So you can come up with a square matrix, and the first row of this matrix is going to be F1, F2, F3, all the way up to Fn. So there's n columns, right? You're going to have n rows because square matrices have to have the same number of rows of columns. So this is going to be F prime, F1 prime, F2 prime, F3 prime, all the way up to Fn prime. And then we'll do F double prime, F1 double prime, F2 double prime, F3 double prime, all the way up to F sub n double prime. And we'll keep going like this down to F n minus 1. Yeah, I think that's how they write them. Yeah. The F1 n minus 1, F2 n minus 1, F3 n minus 1. This is the n minus first derivative of each of these all the way up to F sub n, the n minus first derivative of F sub n. Okay. That is a square matrix. Okay? 1, 2, 3, 4, 5, n columns. You have 1, 2, 3, 4, 5, n minus 1, plus one more is n rows. Well, these are your derivatives, and you have n minus 1 of those plus the 0 derivative. That's your function itself. So there is a square matrix. Okay? Now, what we're going to do with that square matrix is, by the way, all these are dot, dot, dots. Okay, everywhere dot, dot. Take a determinant of it. Okay. And this is called the Wronskian. The Wronskian of this set of functions, F1, F2, F3, all the way up to F sub n. Okay? Now, if that Wronskian, with all these derivatives in it, is equal to that determinant, is equal to 0, they're not linearly independent. Okay? The Wronskian determinant, okay. Okay. The Wronskian determinant is named after the Polish philosopher and mathematician Józef Maria Wronski. Okay. Lived back 1778. That was just after the Revolutionary War here in the U.S. and up to 1853, just before the war between the states here in the U.S. So pretty much the beginning of our country, he was over in Poland doing all sorts of great math stuff. So here's the theorem 413, the criterion for linearly independent solutions. Okay? It seems like they just threw this out there and said you can use it, but they don't tell you how to use it. So maybe this will. And I can't write so much on the screen, so I've got to erase this. And here's theorem 413. Let y1, y2, y3 up to yn. Okay? Be n solutions okay, of the homogeneous linear nth order differential equation, DE, on some interval I. Okay? Now this is that equation 6 we ran into last time, which you turn back a couple of pages under 4.1.2. They had the homogeneous nth order linear nth order differential equation where it's equal to 0, and the non-homogeneous where it's equal to some g of x. That is a solution to the homogeneous one there. Okay? All right. On that interval I. All right. That's the given. That implies then the set of solutions okay, is linearly independent on I if and only if. And usually the symbol I use for that is this one. If means it goes one way, only if means it goes the other way, okay? They also sometimes in math will use, if they're being real lazy, IFF, if and only if. Doesn't quite fit, but you get the general idea, okay? If the Wronskian of those functions, y1, y2, y3, up to y sub n, okay? And the Wronskian is the determinant of the functions, derivative, first derivative, second derivative, third derivative, up to n minus first derivatives. That thing. If that Wronskian is not equal to 0 for every x in the interval. In I. Okay. So that's how we use the Wronskian. Frankly, it seems like a lot of work to me. Okay. Depends on how big the set is. If that was 15, then you have 15 functions. You got to take 14 derivatives, set it up, and then you have to determine the determinant of that. Yeah. But if it's 2 by 2, 3 by 3, that's not too bad. Okay. When they get really big, that is tough to do. But it's tough to figure out whether they're linearly independent for a whole bunch of them too. So this is actually mechanically an easier way to do it. Okay. Now it follows from this theorem that we just did, this one right here, that when those functions are in solutions for that differential equation on the interval I, the Wronskian is either identically 0 or never 0 on the column, on the interval. Okay? Thus we can show that the Wronskian not equal to 0 for some x0 on I, then the solutions are linearly independent on that interval I. Okay? All right, it's not exactly an example, but it's sort of is, okay? It's a for example, okay? Here's two functions. First of these, y1 of x is equal to cosine of 2 log x over x cubed. And here's y2, the sine of 2 log x over x cubed. All right, two functions. It says those two functions are solutions of this differential equation. X squared y double prime plus 7xy prime plus 13y equals 0. Homogeneous, linear, second order differential equation. If it's a second order differential equation, if you can come up with two solutions, especially if they're linearly independent, that's all you really need. Okay, because all others will be formed from those. So we want to see if that works. Now they claim it's the solution, and I'm trying to figure out if I really want to take their word for it or verify it. They kind of stink, but let's do them. What we have to do y1 prime, and what would that be? I'm going to rewrite this as cosine 2 log x, x to the minus 3. I'll write that in front. X to the minus 3. And not do it that way. Okay, because I just like, when I'm taking derivatives, I like to use I hope I'm not erasing too much here. Okay. I'd rather not use denominators if I can write them otherwise. I may regret that, but I think so. So let's take the first derivative of that. It's a product rule thing, so how would you do that? Negative 3x to the what? Yes, to the negative 4 times cosine of 2 log x, because you took the derivative of the first times the second, plus x to the minus 3, okay, a negative sign, so let's make that a minus there, of 2 ln of x times what? Times 2. Anything else? Over x. So that makes it to the minus 4 too, doesn't it? Okay. All right. That was a lot of fun. Now we got to do it again. y1 double prime will be equal to what now? Say again? Oh, okay. Okay, times cosine 2 log n 2 log n x. Okay. Say this again. What you doing now?
Plus 6.
Okay, I see what you're doing. Plus 6, okay. The plus, because when you take the derivative of cosine, it's going to be minus sign, okay. And 2 times negative 3, so 2 times 3 is 6, okay, got that. X to the negative 5, sine of 2 ln x. That was fun again, wasn't it? Okay, but that's just the first term derivative. We've got the second one to do, and that will be, say that one more time. Minus, is that what you're saying? Yeah. x to the minus 5, did you say? Sine, right? Sine of 2 ln x. Another minus.
And that 8 is a plus, right?
Okay. All right. I thought you told me it was minus, so let's see.
It was minus, but then when you took the derivative of x to the negative 4,
right,
it's another minus, so it's a plus.
Okay, so that became a plus. All right.
But the other one is minus, and another minus, and another minus. So minus.
Minus, okay. All right. Wait. All right. Okay, wait. All right, this one was minus. Okay.
Yeah, it was minus 3.
Yeah. And then,
you multiply by minus 4.
yeah, so minus 4 times minus 2 gives you plus 8. Right?
Yeah.
Okay, x is minus 5. Right?
And the other one's going to be.
And yeah, but this sign there just stays the same. So that, I think, is plus.
Yeah.
Okay, now this one.
This one's going to be minus because you have negative
Okay.
times the negative times the negative, the derivative of sign.
Okay, but wait. Where are you getting the negatives? The minus 2 is there.
Oh,
This
yeah.
term stays exactly the same.
You're right, it's going to be cosine as a positive. I was taking the derivative.
Yeah. Derivative of sine is positive. So I think that's, you're right, it stays minus, but it's only because there's one of them. Okay. Minus 2, well, wait.
No, plus.
Okay. All right. All right. Let's start over then with the second part. Okay. You got that. Okay. There's already a minus here. Minus 2. The minus 2 x to the fourth doesn't change it because you're using that, right? How's the derivative of that? Well, the derivative of that would just be positive cosine and then 2 over x. So there's nothing else there. So it's a minus, doesn't it? I think so. I hope so. Okay. But you'll have a 2 from in here, so that's going to be a minus 4, right? And x, it was a minus 4, but then you'll get another one, so it'll be a minus 5. And then it'll be a cosine 2 ln x. Okay. I think we got them done. Let's see what we got. Every term has an even coefficient. So we could pull out a 2. Okay. Every term has an x to the minus 5. So we could pull that out. Right? So I think that's all we can pull out. What you have left here is a 6 cosine 2 log x. And over here you have a minus 2. So that leaves you 6 minus 2 would be 4 cosine 2 log x. Am I right? Okay. And then with the sines, you have a 3 and a plus 8. No, 3 plus 4 is 7, right? Plus 7 sine of 2 ln x. Now, I probably shouldn't have pulled out the 2 x's minus 5, but it just makes it easier to do a little bit. Okay. Now,
Is that why the x squared y double prime plus 7xy prime plus 13y?
Yeah.
That's y1 or y2?
that's supposed to be both of them. They're both supposed to be solutions to that. So we could right now stop and plug in here. And I was just going to suggest that because we've got 2 minutes left. So the x squared is going to knock this down to n x to the minus 3. Okay, but then the rest of it's going to be just like it is. The 7 here, the x is going to knock that down to x minus 3. We could have pulled those out too if we wanted to. I didn't. Okay. And then this one, x minus 3. Okay. And then this one started off with an x minus 3. So they're all going to have the x minus 3 sign. So all we have to do is look at the sines and the cosines. They're all that is this. So let's see what we've got then. And this, I'm going to move these back together. That gives you 8 cosine that. Okay. Plus, and here we have minus 3 times 7. So that's going to be minus 21. And then that gives you 13. 13 and 8 is 21, minus 21. That works. So let's do the sines now. The sines were 14 for the y double prime. 7 times 2 is minus 14 there.
There's no signs of the original.
And there's no sign of the original. You're absolutely right. So sure enough, that does give us make that one 0.
So what is this for?
Huh?
What are we doing this for?
Okay. We're ultimately trying to show they're linearly independent. Okay? So what we need to do is the Wronskian. But while we were doing, I just wanted to first, okay, none of this is totally wasted. Okay? Because what I was first doing is verifying that's the solution. We did that. We're going to do the same thing here, and I'm pretty sure it's going to come up being the solution too. Okay? They said it would. I'll take their word for it. But then in the Wronskian, we'll use y1, y prime 1, and y2 and y2 prime. We haven't done that yet. That will set up our Wronskian. We do the determinant of that. That is the Wronskian is the determinant of that. And if that's not 0, then they're linearly independent. So you see, taking the derivative, the first derivative anyway, is not wasted. The second derivative, we're just verifying it works. Okay. They didn't tell us to, but I just wanted to show you again how we go about doing that. And then the main part is to see if they're linearly independent. And then y1, y1 prime, y2, y2 prime, that determinant. If it's not 0, they're linearly independent. If it is 0, they're not linearly independent. They're dependent. Now, you going to take that home and finish it? Or you want to do it in class next time?
The other side?
Huh?
The other side too?
Yeah. And then the Wronskian.
Oh, the Wronskian. Oh, we'll do that.
Okay, we'll do that in class?
Yeah,
okay. All right. So I'll make my mark here. We'll start with the Wronskian here. Okay. We'll go back and do the first derivative. Well, you've got in your notes y1 and y1 prime. We'll do y2. We already got y2. We'll just do y2 prime. Then we'll do the Wronskian. We won't verify y2 is. We'll take the word for it. Okay, and we'll pick up there. Let's see if we got enough done to do any more homework exercises. I bet we did. Okay, and that would be, ooh, this is a long section. Any of the odds 1 through either 1 or 3, either 5 or 7 or both, do 9, do 11, do 13. Homogeneous equations, do any of the odds 15 to 21, and I guess stop there. Yeah, 15 to 21, and we'll stop there. Okay, good deal. Have a good weekend. We'll see. Oh, yeah, you're going to stay here. But have a good weekend. I've got to run because I've got to head and pick up a car. Okay. So let's save this.